Hello, everyone. So in our last lecture, we learned a couple of important theorems, one of which is the rational zero theorem. And as you may remember, the rational zero theorem helps us to list the possible rational zeros. And that theorem says if we have the polynomial given by this format, and if the coefficients are integers, where an is different from 0, then, and of course, if p over q written in the lowest term is rational 0 of f, then p is the factor of a sub 0 and q is the factor of q sub n. So this way we can list all the possible rational zeros of the polynomial. And of course, we have other theorems like the fundamental theorem of algebra, linear factorization theorem, and so on and so forth. But for example, coming back to this one, based on this theorem or using this theorem, let's say, for example, if we have a polynomial which has coefficients bigger than this one, then the list may get bigger and bigger. Okay, and it's, well, of course, it's difficult to try each and every number or each and every potential zero of the polynomial, because when we have hundreds of them, then we cannot try each and every one of them. So what we need is some techniques or other ways to reduce the list of the possible or the potential rational zeros of the polynomial. So we have the theorem in which we are going to cover it today, which is called the Descartes rule of science. And this one helps us to eliminate or to reduce the possible rational zeros of the polynomial. And this rule of science says if we have the polynomial f of x with real coefficients and a non-zero constant term, then we have two possibilities. One is the number of positive real zeros is either the same as the number of sign changes, this is important here, sign changes in f of x, or less than the number of sign changes in f of x by a positive even integer. Okay, for example, in this case, if the sign change is 5, okay, if the sign change is 5 in f of x, of course, then the possible rational zeros will be 5, or based on this one, based on the second possibility, less than the number of sign changes, which means less than this one, by a positive even integer. A positive even integer less than this one is 1 is 2, 1 is 4. So if we go 2 lower than this, then it will be 3, and then 2 lower than this is 1. So the possible positive real zeros will be 3 or 5 or 3 or 1. Okay, and the second one is the number of negative real zeros is either the same as the number of sign changes in f of minus x. Okay, here it was f of x, and now we check f of minus x and we count the sign changes. So the negative real zeros will be the same with that number, or less than the sign changes of this function by a positive even integer, similar to this idea. Okay, but the thing is, here we count the sign change of f of x, but here we count sign change of f of negative x. So this way we can reduce the potential or the possible number of rational zeros of the function or the polynomial. For example, let's consider this. H of x is given by this function. Now, the first thing that we need to do is we count the number of sign changes. So here the first term is negative and the second term is positive. So we have one change. When we go from the first to the second, we have one change. And then from the second, which is positive, to the next is negative. So we are going from positive to negative, and there is a sign change. So 2, and then from negative to negative. So there is no sign change here. We don't count it. Now here we're going from negative to positive. So we have a change. We have a change from positive to negative and from negative to positive. We just count these signs, okay? Therefore, how many do we have? We have 1, 2, 3, 4, and 5, okay? So determine the number of possible positive real zeros. Remember? Positive real zeros. So the positive real zeros, we count the sign changes in f of x. And in our case, it's not f, it's h of x. So in h of x, the sign changes are 5. So we have 5 sign changes in f of x. So the possible positive real zeros will be 5 or 3 or 1. And these two they came from this definition or this statement, okay? Because it's less than the number of sign changes in f of x by a positive even integer. That's another possibility. So it's either 5 or 3 or 1. And determine the number of possible negative real zeros. And to determine this, we evaluate h at negative x. We need to find this guy. And this one will be negative 4 times negative x to the power of 9 plus and so on and so forth. So we evaluate all those things and we get this, okay? So we have this, and the change will, they start at here because all these are positive, so there is no sign change. But here we go from from positive to negative, and then from negative to positive, so we have 2 sign changes, okay? Therefore, based on the first statement, equal to the sign change in f of negative x, in this case, f of negative h. So it could be 2, or based on the second statement, less than the number of sign changes in f of negative x by positive even integer. So positive even integer is, we subtract 2 from here because that's the next even integer. Therefore, it becomes 0. So either we have 2 negative real zeros or none, okay? And now, when we list the possibilities for the number of positive real integers, real zeros, the possibility is 5, 3, 1, okay? Ignore this one for now. That's the possibility, right? So we have to write the combination, right? So here we have, and for the second one, we have either 2 or 3 or 0. So we write this combination. Okay, let me put it this way. For the positive, this is for the positive, we have either 3, 2, or 1. For the negative, we have 2 or 0. Okay, so I will write this in combination. We combine all together. This one, this one, this one, this one, this one, this one. Therefore, we have 5, 2, 3, 2, 1, 2, 5, 0, 3, 0, and 1, 0. So this is what we have, the first 2 rows. Okay, the first rows are exactly this one, just combination of these things. Now, these 2 lines, the first 2 lines, are about real zeros. Okay, one is for positive and the other one is for negative, but both of them they are real zeros. And if we add this, what do we get? This is 7, this is 5, this is 3, this is 5, 3, and 1, if we add the total. So in total, because the possibility is either this one or this one or this one or one of these 6 possibilities, so in total we have either this or this or this or this or this one or this one real zeros. But looking at the degree of the polynomial, it's degree 9, and including the multiplicity, if we count the multiplicity of the zeros, we expect this polynomial to have 9 zeros, right? So we have to make this equals to 0 when we add this, right? So in order the sum to be 0, that means we have some imaginary zeros. Okay, we have some imaginary zeros of this one, because the sum of the negative and the positive real zeros, they don't add up to 9. That's why we know there exists an imaginary zero or some imaginary zeros. Okay, therefore here we have 7. So to make that one 9, we know there are 2 imaginary zeros. So in total we will have 9 real zeros, including the multiplicity, that means. Okay, and if the possibility of negative and positive real zeros is 3 and 2, then that's 5. Therefore, we need to add 4 imaginary zeros so that we can have 9 in total, and so on and so forth. So as you can see, the last row is the sum, and all of them, they are 9. And it's just 9 minus the sum of these 2 rows to find the last row, or the third row, to find the number of the imaginary zeros. Okay, so this is how we can determine the possible positive real zeros, possible negative real zeros, and imaginary zeros. Okay, and another way, or another thing that can help us reduce the potential or the possible rational zeros is that to find the upper bound and the lower bound. So the upper bound is basically if we have a list of possible rational zeros, and if all the zeros of the polynomial are, let's say, less than this number, then we call this one an upper bound. And if all the real zeros are greater than this number, then we call this number a lower bound of the real zeros. Okay, so basically that's what it means. So for example, if we have this graph, the zeros of this graph are the points where the graph touches the x-axis. For example, we have here, this one, and this one. So those are the zeros. So I can say this is the upper bound of the real zeros of this polynomial. And I can say this one is a lower bound of the real zeros of this polynomial. Okay, and the formal definition of upper bound and lower bound is given here. So suppose we have the polynomial f of x with degree greater or equal to 1, and real coefficients and positive leading coefficient. The leading coefficient has to be positive. And further, f of x is divided by x minus c. Okay, so all this is assumption. We're assuming this is true. So if c is greater than 0, c is this number. If c is greater than 0, and if both the remainder and the coefficient of the quotient and the are non-negative, then c is an upper bound. So in order c to be upper bound, once we divide f of x by x minus c, and if the coefficient of the quotient and the remainder, if all of them are non-negative, then c is an upper bound. We know c is an upper bound. Okay, which means basically all the rational zeros or the real zeros of the polynomial are less than c, less or equal to c. Okay, and if c is less than 0, if this is negative, and if the coefficients of the quotient and the remainder alternate in sign, if they change, like positive, negative, and so on, or negative, positive, so c is a lower bound for the real zeros of f. Okay, so this is the concept of this upper and lower bound. So we can determine whether c is an upper bound or a lower bound. So if we know c is an upper bound, let's say we have a list of possible rational zeros, let's say, for example, plus or minus 1, plus or minus 2, and so on, plus or minus 10, and so on, so forth. So now let's say if I know, based on this definition, if I know 5 is an upper bound, if we know 5 is an upper bound, let's say we have plus or minus 5 here. So if I know 5 is an upper bound, then I can ignore all this, okay? Because I know this polynomial, the polynomial, whichever polynomial it is, I know the polynomial, the upper bound of the real zeros of this polynomial is 5. So all the polynomials, well, not all of them, just the positive, of course, just the positive, because we have the negative, so we will have the negative 10 on this side. But the positive, I will omit them. And similarly, on the lower side, once we find the lower bound, then we can reduce, or we can cut off all the possible rational zeros below the lower bound. So that's how they can help us narrow down our options. For example, we have f of x given by this, and we're asked to determine whether 6 is an upper bound for the real zeros of f of x. So based on this one, as you can see, 6 is positive, which is this one. In our case, c is 6 here. So using the syntactic division, we divide this function by 6, and we have this. So these are the coefficients of the quotient, and this is the remainder. Okay, here is the remainder. We put it in a square. And as you can see, all of them are positive. The coefficients are positive, and this is positive, and this is greater than 0. 6 is greater than 0, C, which is C in this case. This is C. Therefore, by the first definition, by definition number 1, we know that 6 is an upper bound. Okay, this number is an upper bound. And again, for the same function, for the same polynomial, let's see if 5 is an upper bound. So we know 6 is an upper bound. If 6 is an upper bound, then of course 7 is an upper bound, the number, because 7 is above it. So all of them, all the numbers greater than this one, they will be upper bound of the polynomial. Okay, so let's see if 6 is since 6 is an upper bound, and let's check now if 5 is an upper bound too. And if we do so, if we follow this idea, if we divide the polynomial by 5, then as you may see, we have the coefficient of the real zero, the coefficient of the quotient, okay? And this one doesn't alternate. As you can see, we go from positive to negative, from negative to positive, but here we have two positives. There is no change, okay? So, and another thing is C is greater than 0, okay? This is our C, and it's positive. And we would expect this one to be positive, okay? If this were positive, then yes. But in this case, this is negative, so we cannot say it is an upper bound, okay? So, and the next is, let's determine if -1 is a lower bound of the real zeros. And dividing this by -1, we have this, and we have the remainder -55. So we have from positive to negative, negative to positive, and positive to negative. And as you can see, all of them, they are alternating inside. Therefore, yes, this is -1 is a lower bound for the real zeros of f of x. So that means I can remove all, or I can omit all the possible rational zeros of the polynomial, and all the possible rational zeros of the polynomial above 6. We can cut them off, okay? That way we can reduce the options so that we can try only those values, okay? And the next is inequalities, polynomial inequalities. So far, we have been discussing the polynomial functions and, of course, polynomial equations. And a polynomial inequality, let's say we have f of x as a polynomial, then an inequality of the form f of x less than 0, or f of x greater than 0, or f of x less than or equals 0, or f of x greater or equals 0, which basically means if one of the inequality signs is included, then we call this polynomial inequality. Okay. Now, let's just go straight into how we can solve a polynomial inequality. Now, solve this inequality. Let's do this one. We have this example. So the first thing that we need to do here is we need to write this polynomial in this form, in one of these forms, okay? Which basically means let's put all the terms on one side so that we can simplify or factorize it. And so to do so, I will write this one as x to the fourth, and the next degree is this one. So moving this to the right side, it will be plus 4x cubed. Moving this one to the left side, it will be minus 3x squared. And we have 18x greater or equal to 0. As you can see, now this is our f of x. This is our f of x. So we have f of x greater or equal to 0, which is this form. Okay. This is f of x greater or equal to 0 format. Okay. And the next is we need to factorize this polynomial. We need to factorize this one. And to factorize it, as you can see, we can factor out the x because all of them, they have x. So factor out x, and that will be x cubed plus 4x squared minus 3x minus 18 greater or equal to 0. And the next is we need to factorize this term with this factor. Okay. And to do so, because this is cubic function or cubic polynomial, what we do is, again, we need to find the possible rational zeros so that we can find out. So by the rational zero theorem, we can list the possible rational zeros, and they will be the factors of this one divided by the factors of 1, and that's basically factors of this because this is 1. Therefore, we will have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. So I'm not going to follow all the steps now here, just to save some time, but I have tried it earlier, and I know 2 is a factor of 0 of this polynomial, okay? But what you can do is you can use the Descartes rule of signs and the upper and lower bounds so that we can cut off some of the possible values, and then we can try one, because we need one factor or 1 0 for this polynomial, because once we find one factor, then the remainder will be a quadratic function and a quadratic equation or a quadratic form. And once we have the quadratic form, then from that onwards, it will be a problem. It's not going to be a problem because we are familiar with how we can factorize or how we can solve a quadratic form. Therefore, I know this is 2 is a 0 of this one, so I'm going to divide it. Let's divide this 2 and the coefficients are 1, 4, negative 3, negative 18, and we have 1. 2 times 1 is 2, Add this 2, we get 6. 2 times 6 is 12. Add this, we have 9. 2 times 9 is 18. And if we add these 2, we get 0, and that's the remainder. And these are the quotients of the quotient, okay? Therefore, I can write the middle term. I can write this expression as one is, since this is positive, I'll write it as x minus 2. And the quotient is this one, which is x squared plus 6x plus 9 greater or equal to 0. Okay, and we keep factoring it, and this is a perfect square, we know that, or we can follow the factorization theorem and we will find out that this is x plus 3 squared. Okay, now we have 3 different factors, including one of them has a multiplicity of 2. And the next is we need to find out the interval where this f of x, or where this function or this polynomial is positive. Okay, that's what we are trying to find out. Solving this inequality means finding this polynomial, the domain of this polynomial, or the interval of x at which this polynomial is greater or equal to 0. Okay, so what we do is we solve this one first. We find the solution to this one, and those will be used as boundaries. So this polynomial will be 0 at x minus 2, x plus 3 squared. I will use the equal sign so that I can find the 0, or the values where this polynomial or this equation or this expression becomes 0. So this becomes 0 at x equals 0, or x equals to 2, or x equals to negative 3. So these are the boundaries. Okay. And the next that I'm going to do is I will draw a line. I will draw a line, and I will put the boundaries starting with negative 3. Let me put it on the, and the next is 0, the next is 2. So now the next is we write these factors one by one. Here we have the factors x, x minus 2, x plus 3. So x, here is one of the boundaries. This is a boundary. This is another boundary. We call this boundaries. And so the first factor, which is x, is on this interval. It's 0 at this point, and it's negative at all the points below 0. Therefore, here it's negative, here it's negative, here it's positive, here it's positive. Okay, x is greater than 0. From 0 to the right, it's positive. From 0 to the left, it's negative. That's obvious, right? And then the second term is x minus 2. And x minus 2 becomes 0 at x equals 2. And I'm going to write it here, x minus 2. So to the left of x equals 2, this is negative, right? Here it's negative, here it's negative, here it's negative, here it's positive. Okay. And the last one is x minus 3. I will bracket of plus 3. I'll put it square. So x plus 3 becomes 0 at this point. So to the left of -3, well, since this is square, it's always positive. So here it's positive, here it's 0, here it's positive, here it's positive, here it's positive. Okay? It's always positive except at this point. And this is 0 at this point. This is 0 at this point. Okay? And the next is, well, now we need to multiply it. I have to change color. Now we need to multiply all this expression, all these factors, so that we can solve for f of x. So the product of, we have for the individual, the signs of the individual factors. The next, what we need is the product. So now we need to multiply it. Okay. Okay. So this is product, right? X times x minus 2 times x minus 3 plus 3 squared. Let's multiply now on each interval. So the first interval is from -infinity to, this is -infinity to -3. Okay. And let me not use that bracket. Just sorry. So here we have negative times negative. Negative times negative is always negative, always positive, sorry. And positive again, if we multiply positive by positive, it's positive. So this is positive. At this point, it's 0 because we have 0 here. So 0 times any number is 0. Here, again, it's positive because negative times negative is positive. Positive times positive is positive. Here, it's 0. Here, positive times negative is negative. Negative times positive is negative. So we have negative. Here, it's 0. And here, 3 of them are positive. So it is positive. Now, the question is, on which interval is this expression positive? That's what it's saying here. Okay. And as you may see, as you can see here, this expression or this polynomial is positive at 3 different intervals. Therefore, the solution set is -infinity to -3 union. I put this close parenthesis, close bracket because we have greater or equal to 0. It's included. And well, I don't need to, okay, let me not divide this. Since it's greater or equal to 0, so I can go all the way to here because these are all together. There is no break in here. So I will go to 0. Oops. Same color. Union. And then from 2 to positive infinity. Okay. So this is the solution to the inequality. Okay. And the next is rational inequalities. Okay. So this is just polynomial inequality, but now we will see what rational inequalities are. And a rational inequality is, suppose f of x is a rational inequality, rational expression. Well, rational expression is something that we write in the form of, we have x term on the numerator, we have x term on the denominator. Let's say x minus 2, x plus minus 3 or plus 3, something like this. Okay. If we have the variable on both the numerator, on the denominator, actually, here we may have, for example, I can have I can have 1 over x plus 3, for example. Still, this is a rational expression. So as long as we have the variable on the denominator in this form, then that's a rational expression. Therefore, if the rational expression is written in this form, then we call it rational inequality. Okay. Now let's see how we can solve a rational inequality. We have this simple example, and we wanted to find where this inequality holds. So the first thing that we do is just similar to the polynomial inequality. We bring all the terms on one side, and I will have 1 over x plus 4 minus 1 over x minus plus 2 greater or equal to 0. Okay, I just bring this one to the left, and we get this one. And the next is we multiply this one by, change color, x plus 2 over x plus 2, and minus 1 over x plus 2 times, and this one we multiply by x plus 4 over x plus 4. Okay, greater or equal to 0. And well, if we multiply this, we get x over 2, x plus 2 over x plus 4. Let me write 2 first, x plus 4. It doesn't make any difference. And then here I will have x plus 4 over x plus 2, x plus 4 greater or equal to 0. Okay. And now, since they have the same denominator, I can add this or subtract them. So we will have x minus x will be 0. X plus 2 minus x minus 4 over x plus 2, x plus 4 are equal to 0. And here they will cancel out, and this is negative 2 over x plus 2, x plus 4 are equal to 0. So we don't have any x on the numerator, but we have this one on the denominator. So still, this is a rational inequality. And of course, the left side is a rational expression by itself. Now, the question is, on which interval that this inequality holds? Okay, for what values of x, or for which values of x does this inequality holds? So the numerator is always the same. It doesn't change. It's always negative 2. So the question is only the numerator. So when does this numerator change sign? Okay, therefore, we will do the same thing. We will solve this. Let me change x plus 2. Well, this will be 0. Let me just x plus 4. This is 0. Therefore, x is negative 2 or x is negative 4. Okay, this will be 0 at either of these values. Therefore, the boundaries are this negative 2 or negative 4. Therefore, negative 2 and negative 4. Okay, negative 4, negative 2. We'll put them in order. And here I have x plus 2. And okay, and the other one is x plus 4. So x plus 2 is 0 at this point, and to the left of this point, it's always negative. Sorry. Yes, it's negative to the left of this one. And to the right is positive. And x plus 4 is 0 at this point, and it's negative on this interval, positive on this interval, and positive on this interval. And the next is, how about x plus 2 and x plus 4? This is product of these two. So on this interval, it's negative times negative, so it becomes positive. Here it becomes 0 because any number times 0. Here it's negative because negative times positive. Here it's 0. Here it's positive. And the next is negative 2 over x plus 2 and x plus 4. Now we are only interested on the sign, okay? We don't care about the values. But since we have the boundaries are from negative 4 to negative infinity, negative 4 to negative 2, and negative 2 to positive infinity. Those are the intervals that we have. And we are trying to figure out the sign of this expression or this rational expression on each of those intervals. And then we will pick out the intervals where this expression is positive, okay? So here, negative 2, sign of this expression is positive. So negative divided by positive is negative, okay? Here, this expression is 0. So it becomes negative 2 divided by 0, negative 2 divided by 0. Remember, this is undefined. Therefore, this is undefined. I will use u for now. Just small u. This is undefined, or I will write undefined like this one. At this point is undefined. Undefined. And here, this expression is negative. So negative divided by negative is positive. And here again, it's undefined. And here it will be negative because negative 2 divided by positive is negative. So this expression is positive only on this interval. Now the question is, what is the solution? So the question is, this is the question. On which interval is this expression greater or equal to 0? Greater or equal to 0 means positive sign. And as you can see, the positive sign is only on this interval between negative 4 and negative 2. And are these two boundary lines or boundary points, are they included, negative 4 and negative 2? Well, the answer is they are not included. And the reason is because at negative 4, the rational expression becomes undefined. At negative 2, the rational expression becomes undefined. So since those two values make this expression undefined, we don't include them in the solution set. Therefore, the solution is negative 4, comma, negative 2, and that's the only solution, okay? Because outside this interval, this rational expression is always negative, to the left of negative 4 and to the right of negative 2. Okay, so this is in generally how we can solve the polynomial inequalities and rational inequalities, okay? And the next is, this is from section 3.7, and this is about direct and inverse variations. And what do we mean by this direct and inverse variation? This is basically a relationship between two or more variables, of course, okay? But first, let's start with two variables. So here, these are the same, y varies directly as x. So there is direct relationship between x and y. That's basically what it means. Okay, direct relationship, which means as x increases, y is increasing. Okay, or we can say y is directly proportional to x. So both of them, they mean the same thing. They have the same meaning. And to write this one in mathematical expression, this first, we can write it as y equals to k times x, where k is a non-zero constant real number. Okay, k is just a constant, and this is called the constant of variation. So if we know they vary directly, if we know y and x vary directly, then we can write y as k times x. Okay, and then the other one is the inverse relationship. If we know y varies inversely as x, then we can write y equals to k over x, or we can write y equals to k times 1 over x, which is the same with this one. Okay, and this is the same with saying y is inversely proportional to x. Now, the graphically to look at this one, if of course the horizontal is x and this is y, and looking at this plot or at this graph, as x increases, y is increasing. In this case, this is t, this is d, not x and y. We have d equals to kt. So this k in this case is the slope. K is the slope of this line. Okay. And here we have inverse relationship. As x increases, when we go to the right, x is increasing, right? But y is decreasing. In this case, this is r, this is t. So as r increases, as it goes from 0 to 10 to 20 to 30 and so on, then the value of t is going down, decreasing and decreasing. Okay, therefore this is what we call inverse relationship, or they vary inversely, or they are proportional. They are inversely proportional. But this one is they are directly proportional, or y varies directly as x. And another one is joint variation. So in this case, we have more than two variables. So if we say y varies directly as y as w and z, or if we say y is jointly proportional to w and z, then that means y equals to k. K is the same, the constant of variation, k times w times z. So as you can see, these two are variables. Again, y is variable. So y varies jointly as w and z, or we say y is jointly proportional to w and z. Okay. For example, if we have the volume v of a right circular cylinder varies jointly as the height h of the cylinder and the square of the radius r of the cylinder. Okay, so we know v, this is one variable, it's varies jointly as h and r. Okay, therefore we know v equals to k. K is the constant of variation, times h times r squared, because it's square of the radius r. So we have r squared. So this is the volume. Just from this one, we can write the mathematical expression. So to solve an application involving such variations, what we do is we write the general variation model that relates the variable given in the problem. And assuming k is the constant of variation, we include it in the mathematical expression. So we solve for k by substituting known values of the variables into the model from step 1, and then substitute the value of k into the original variation from step 1 again, and use the variation model from step 3 to solve the application. So let's look at this example, and we follow the steps. The amount of pain reliever that a physician prescribes for a child varies directly as the weight of the child. Okay, so as you can see, the variation is directly, which means they are directly, they have direct relationship. A physician prescribes 180 milligram of the medicine for a 40-pound child. So this is W, and this is the prescription. Okay, so the first thing to do is we need to write the expression. If we write this one as A, this is A, just variable, and this is W. So since they vary directly, we write A equals to K times W. Okay, so this is the first thing that we do. We write this one in mathematical form, and then we solve for K. Okay, so A is 180, W is 40, so we have 180 equals to K times 40. Dividing both sides by 40, we get K equals to 9/2. So that's K. Therefore, we replace this one in here, and we get A equals to 9/2 W. Now, to answer this question now, we use this formula. So how much medicine would be prescribed for 50-pound child? So this 50 pound is W. So we just substitute this value in here, and we find the amount of medicine prescribed for this child. So 9/2 times 50, it becomes 225 milligram. Okay. And how much would be prescribed for a 60-pound child? Well, we just substitute 60 in here, and we get 270. And similarly for 70, we get this one. And the next is, if 135 milligram of medicine is prescribed, what is the weight of the child? So here is the other way around. We are given the value of A, but we don't know the value of W. So we plug this value in here, and we have the formula that A equals to 9/5 times 9/2 times W. So we have 135 equals 9/2 W. We multiply both sides by 2/9 so that we get rid of this. And we have W equals to, if we simplify this, we get 30 because this is 15. Okay, so the child will be 30 pounds. Okay, all right, so this is all about this lecture, and see you in the next lecture.